So the colours aren't just spectral colours. They're not just colours you see in the rainbow. And it's connected to last week's talk. I'll take you through the details. So if you are sort of year 10 or above, you're about 15, 14, you should be okay. I think it's just going to be optics, it's going to be some refraction, and you should be all right. We have a film. Thickness D. Oh, if you like algebra, you'll love it. Right. Thickness D, and D is a thin film. I'm going to tell you exactly what thin means in a moment. It's going to mean a lot different to perhaps your preconception of what a thin film is. And I'm going to look at, for a soap bubble, what the refractive index is. And the refractive index is a measure of how light bends when it goes into the film. For our purposes, we're going to aim the light straight down. So for us, it's a measure of speed of the light in the film. And N1 is the air, so that's got a refractive index 1, very close to space, so empty space, so 1's good enough for us. The bubble, it actually really is more like 1.4, but 1.5 makes the maths easy, so we're going to say 1.5. It's an okay approximation to make. And air is 1 again on the inside of the bubble, or we could just have a film like on my circle. So I've got some light coming down, and I've drawn the wave fronts. These are the peaks of the waves and the waves of light that are coming in and out of the page. But there's no need for it to be like that, it's just to make it clear. So it's not, those people who know what I'm talking about, it doesn't have to be polarized, but I've just done it like that. So I can draw it in 2 dimensions. So there's our rays hitting the soap film. And when it hits the film, there's a law that determines how much of it reflects and how much of it goes straight through and refracts. This isn't going to refract strictly because it's going straight down, so this is a special case where it's just going to go straight down. The sin I will be 0. Right? And you can see that clearly because you can see my face through the film. You can also perhaps see colours. I can see colours, so some light is going through, some light is reflecting. I think that's clear. Now, the rule is a little bit complicated. It's that there. And it means that this is the intensity of the light that comes back. And it's, I'm going to give it as a percentage of the light that's gone in at the start. It's this rule. So you take the first refractive index, you take it from the second, then you, on the bottom, you add them. That represents the amplitude of the wave, what you know as the peaks. And if you square it, you get the intensity, which is sort of loosely related to the brightness, but it's not related to the perceived brightness, as last week's talk mentioned. So you see different colours, different amounts. Now if I start off with, oh sorry, I thought to say that if you don't like that, if you're saying, hey, that's not fair, I thought you were going to show us, you're going to derive it for us. If you don't like that, you think that I should explain that, well, that's the explanation. That's for Nernst equations. And I'm sure now the other one doesn't look so bad. So this is just to scare you. And we do the same, but we add it instead. And we square it. And we actually get minus 0.2 squared. Which is kind of weird. Because if you think about it, I said that the stuff inside the brackets represents the amplitude of the wave. And now we suddenly have a minus amplitude. And you're told that amplitude is the maximum displacement for a wave, right? So negative amplitude. Pretty weird. Well, it turns out to be okay. What it represents is, upon reflection, the wave flips. And later I'm going to say that the phase flips. And that's an animation at the top. But down below is a video with many frames per second taken from Salford University of that exact thing. And I click here, you see it nice in slow motion happening for real with a rope. And you notice as it hits the boundary, a peak becomes a trough and a trough becomes a peak. And that's what that means. Right. So we've done that, we got minus 0.2, but that's cool, we'll remember that later. We need that for later. But if I do the maths, I figure out that minus 0.2 squared gives you 0.4, so that's 4% of the light. So I've got 100% coming in, I get 4% out, 96 goes straight through. Right. Next stage then is to figure out what happens at this second boundary, and this turns out to be the whole reason that you get the colours. Because at this boundary, some is going to reflect, some is going to go straight through and refract. And we do the same game again, but this time we do our 2 to 3. We're going from medium 2 to medium 3. We put the numbers in again, and this time we get positive 0.2 squared. So again it's 4%, but there's no flipping around. And if I do the maths again, I figure that I get 4% coming back, but it was 4% of 96%, so I counted that in. And then the rest goes straight out, so we forget about that, I don't care about that. And I now want to finally look at this 3.84%, how much of that gets out, finally, to where you're standing to see the colours. And I do the same maths again, but this time it's from 2 to 1. We had 1 to 2 at the beginning. So this is 1 to 2, this was 2 to 3, and now this is 2 to 1. And I do the maths again, and this time I get 0.2, and it's positive at that boundary because it's going the other way. So I get 4% of whatever that was, which is 3.82, and I get 0.02 coming back. Now I'm going to stop there, I'm not going to do it again, because I could do it again. I could do, well, how much goes through this time? But that's boring, and we've got 0.02%, so we'll forget about it. You know, we're all friends here, we'll just leave it alone, it's fine. So we get finally, and that was due to Walter Lewin at MIT, so thank him for that. These two then reach you at pretty much the same time. And if you keep the light on for a long enough period, then those two different reflections will keep coming at you. One we have at 4%, one we have at 3.82% of the intensity, and it's interesting then to try and figure out what those two waves of light do when they combine, and you see them with your eyes. Now, the tricky thing to remember is that inside the film, the wavelength reduces, right? Inside the film. And that means then that whatever happens in here determines what comes out. And the wavefronts, although were all straight at the beginning, when you look at, and I've just simply displaced this, so don't get confused, I've just put one here, one here, one here, but they obviously all happen in the same line. And I forgot to mention that, I moved them over so I could spread out for you to see. So these are both one on top of the other, and we're going to try and compare them. The second one then may very well be a little bit of a step out. It may not be in the same place. The wavefronts there may be a little bit above or below because of the extra path it travelled. This one reflects straight back. This one had to go through all this stuff to get out again. And depending on the thickness, that will depend upon where these wavefronts arrive. So next we have to figure out exactly how much out of step that one is with the other one. To do that, we need to understand how we represent waves. Now, waves are quite tricky to represent with mathematics because we have this thing called the amplitude, and that changes over time. So you can use a cosine rule, but you could equally, you could use cosine to do it, because that certainly undulates back and forth. But another way you could do it is you could say, well, this amplitude, and this is the peak of the wave going back and forth like that, we could represent that with an arrow. And if we have the arrow spinning around, we can then say, well, we'll just take the bit that's going along here. So if the arrow's up here, forget that if you don't understand it. But if I click here, you'll see what I mean, hopefully. That's not good. That moved very quickly. Well, if you concentrate really hard, you'll be able to see it. It's moving quicker than I thought. And the idea is that the wave can then be represented by this idea. And if we think about how fast this arrow is going around the circle, we can get this thing which is called it's omega, and we use that to then determine the properties of the wave. If that was unclear, then this will help. We're going to try and add two waves. We're going to try and add two waves together. So we're going to add the one that reflected off the front surface, the one that reflects off the back surface. We're going to add those together and then see what wave comes out. And this is going to be even more trippy because we've got loads more lines. But stick with it, you'll get it eventually.